Welcome to the third video in Dynamic Systems and Control. And what we're going to be doing is we're going to be taking that bond graph that we designed in the last video, and we're going to be going through and creating an equation for its representation. First, we need to start out at the left end, SE, and we need to know what the force and the velocity are at each point. So we're going to say we already know what the force is at SE. It's going to be F. We also kind of know what the velocity is at that point. It's going to be x2 minus x1 over the change in time. x2 minus x1 is the displacement. Over time is going to give us the velocity, right? So we're just going to have that be a representation as delta x dot. Delta x dot is going to be known as the velocity. Next, we know that we're at a one junction, so the velocity is common for every single component. So we're going to label each of these components delta x dot, delta x dot, delta x dot. As you can see, that is a representation of system over here. Next, we need to know the force that's generated at the capacitor. Well, we know that force is basically the spring coefficient times the displacement. So that's going to be K times the displacement delta x, not delta x dot, just delta x. Next, the resistance is going to be B times the velocity. Lastly, we're stuck with the mass, and mass is representative of M, and the force of the mass is going to be M. The change in the velocity, which is M acceleration. M times acceleration is going to be the force. Acceleration is the derivative of velocity. Change of rate of velocity over time is acceleration, so we're going to do a double dot there. So we have all the forces defined right here, and we have all the flows defined right here. So the sum of the forces that are going into a one junction needs to equal 0. And the reason is because if they were not equal to 0, then these masses would accelerate in different rates, but they don't. They accelerate at the same rate because we already specified that they're at the same velocity. So how we write this equation is going to be, we're going to sum all the forces. If the force is going into the system, then we're going to say F is positive F, minus the resistor, which is going to be B delta x dot, minus K delta x, minus M delta x double dot, which is going to equal 0. So if we solve for F, then the force is going to equal B delta x dot plus K delta x plus M delta x double dot. What can we do with this? A number of interesting things. Given a force, we can calculate x, the displacement. We can also calculate the velocity of the displacement with x double dot, given an initial condition. We can calculate the acceleration. When we solve for x, we know the displacement given a particular force. We know how much the system is going to move given a particular force. This is the representation of that function, given different spring constants, different dampener constants, and different masses. And that's the power of bond graphs and the introduction to dynamic systems and control.